Now there's a couple other classes that we should talk about of our systems. The first is whether the system is causal or not. Now causality is an idea we introduced with signals a while back, but it also applies to systems. Causal systems are also known as non-anticipating systems. And here's how we define them. At any moment in time, t0, we'll call that the present moment. The output of the system, that would be y of time t0, is determined completely by values of the input signal x of t that arrived at the system either at the same time as the output, at that instant t0, or at some time prior to that. So the output is dependent on the current and previous inputs. If that's true, and if that's totally the extent of how the system operates, it is a causal system. If that's not true, then it's a non-causal system. The main thing is causal systems cannot rely on future information to determine the current output of the system. We can't need any future values of the input signal, like x of t plus something, to determine the present output y of t. So causal systems don't use future values of the input. How do we look at the differential equation and spot causality or non-causality? If our differential equation is written in terms of y of t and y prime of t and y double prime of t, we cannot have any x terms that are functions of t plus tau, representing a time advance or a future value of an input signal. Again, here's a place where time compression and expansion terms can also mess up causality as well as time invariance. So if we have, for example, a y of t equals x of 3t, that's a time varying system. It's also a non-causal system because, for example, we could plug in time t equals 3 seconds. In that expression, then, y of the time 3 seconds is determined by x at 9 seconds. It hasn't arrived yet. On the other side, having fractional time scaling is also a problem. For example, if y of t equals x prime of t over 2, then for negative values of time, like y of minus 4, that equals x prime of minus 4 over 2 or x prime of minus 2. So computing the value at 4 seconds before time t equals 0, I need the value at only 2 seconds before time t equals 0. This is an input that happens later than this output. So compressions and expansions can't be part of our defining differential equation to have a causal system. So let's put these all together now. Here's a simple equation. Y of t equals 8x of t plus 3. Is this static or dynamic? It's a static system. Is it linear or nonlinear? Well, definitely nonlinear from that plus 3. Is it time invariant or time varying? No functions of time, no time compressions, so it's okay that way. It's time invariant. And is it causal or not? Well, no t plus anything on the x side here, no time compressions or expansions, so this is actually okay as a causal system. So this is a nonlinear, static, time invariant causal system. Here's one that y of t equals 2t plus 1 times x of t. Now you might think this t plus 1 out in front, that's like a different time, might mess up this being a static system. But in fact, it is static. The current output, y of t, is determined only by the input signal at the time, the same time t. This is just a multiplier out in front. The multiplier happens to be changing with time, but at any moment in time, if I know this equation, I know what the value of time is, and I can just plug it in here. So it's not indeterminate. In terms of linearity, this would still be a linear system. I don't have any x squareds, I don't have any offsets, don't have any cross products. It's definitely time varying because I don't have a numeric constant out in front here. I have a function of time out in front of my x, so it's time varying. And similarly to the argument we made about this being static, this is a causal system. I have a t plus 1 here, but it's not a time argument for my x or y. It's just a multiplier. And so it doesn't represent future information. It's just a time-changing value. I just need x of t at the current moment of time to figure out what is y of t at the same moment in time. I don't need future information. And so this is a causal system. Here's a second-order system. I have a y double prime of t. On the left side, nothing out of the ordinary here, although because I have a derivative, it's definitely a dynamic system. Here we have a 3 times x of t plus 1, 2x prime of t. In terms of linearity, I've got constant coefficients, so we're okay there. For time invariance, well, this represents a time shift. It's not a compression or expansion. No time arguments in front of my x's or y's, so this is actually a time invariant system. However, it's not a causal system. Y prime of t computed at time t requires a future value, x of t plus 1. So this is a non-causal system. Now, why do we care so much about causality and non-causality? We know we need systems that are linear and time invariant for the analytical techniques we're going to use. Do we have to have causal systems for our techniques? Well, no, not always. We're going to assume our systems are causal most of the time, however, because in order for a system to be physically realizable, meaning I can build one in the real world, it has to be causal. We can't build non-causal systems. We can't make systems that anticipate the future, that need future information in order to operate now. If we could, we'd all be winning the lottery and we'd be doing something else other than being in class right now. So linearity, time invariance, static and dynamic, causality. One last property that we're looking for, one last classification for our systems, and that's whether or not they're stable. Now, that's going to be an important concept for us. We're going to want our systems to be stable, so we're going to need a good, sturdy definition for what is stability. And at the beginning here, we're going to have to start with a definition that's going to feel a little unsatisfying, a little bit too wide open. But it'll be our starting point, and we'll build from there and come up with some explicit criteria that enable us to determine whether a system is stable or not, even by simply looking at its differential equation or its system operator. The concept of stability is one that if I put any reasonable signal into my system, if it's stable, the output shouldn't go taking off towards infinity. Now the issue is we have to describe and define mathematically what is a reasonable signal, and what do we mean doesn't take off to infinity. So here's how the mathematicians do that. Let's define x of t as a bounded signal. And a signal is bounded if its absolute value has some value less than a constant m. And that has to be true for all time. As long as m is anything smaller than infinity, the signal is bounded. So m could be 10 billion, but if the absolute value of x of t remains less than 10 billion, it's got a boundary. It's bounded. We'll call a bounded signal a reasonable signal. So a system is stable if I can put in any bounded input signal to my system and get an output response that is also bounded. If that's true, I will say I have a bounded input, bounded output, stable system. BIBO. And we actually literally do use that acronym, BIBO stable, as our shorthand for this concept. My system is stable if I can put in any bounded input and get an output that's also bounded. Now the output doesn't have to have the same boundaries as the input. The output signal could be bigger than the input, but as long as it remains bounded, as long as it doesn't go shooting off to infinity, that's okay. So if x of t is bounded by some boundary value m for all time, and I put that into my system, y of t also has to be bounded by some other boundary, call it m prime. Both of those boundaries must be less than infinity. If that's true, then my system is bounded input, bounded output stable. Now, how do I look at a differential equation describing a system to tell whether it's stable or not? For that, we're going to need a little bit more system analysis understanding and a few more mathematical techniques. So for the moment, we're going to have to hold here at the level of sophistication of our methods for determining stability. But we can look at this and see an example how this could play out. Let me make a system whose job is to do an integral. And we saw actually yesterday that there's a simple circuit configuration, an op-amp with a capacitor in its feedback loop that acts as an integrator. And so this is a practical circuit. If I had such a circuit, an integrator circuit, we'd want to know, is that a stable system? So if y of t is related to the input signal as a running integral from -infinity to t of x of t, is that something that's bounded input, bounded output stable? In order to prove that it is or isn't, all I need is one signal, example, one bounded input signal that produces an unbounded output with that system. And if I can find that one signal, it's not stable. The opposite is harder to prove. Easy to prove a system is not stable. I just need one example to disprove it. Harder to prove that it's BIBO stable because I would have to test every possible bounded input signal. So we can rule systems out, but hard to rule them in. In the case of an integrator, there's a very simple bounded input that I can apply and prove that an integrator is an unstable element all by itself. If my input signal is a unit step, and my system integrates that, so the integral of a unit step, well, integral of 1 dt is t. And that is a ramp function, which will go off to infinity, and if I could keep going forever. And so, since there's one example of a signal that makes this system go off to infinity, this is not a stable system. That doesn't mean it's not a useful system. I might be able to use this as an element, as part of a system, but if using an integrator by itself is kind of a dangerous thing if you might be inclined to putting step functions into it and holding them there for a long time. So an integrator is not BIBO stable because there's one bounded input that did not create a bounded output. Now these properties, and particularly the properties that go along with linearity and time invariance, are actually the foundations of many of the analytical techniques we're going to come up with to analyze our continuous time systems. A lot of them involve the idea of predicting the system response to an arbitrary input by decomposing that input into sums of simpler functions like we were doing yesterday. But I'm going to be particular in the kind of simple functions that I choose. I'm going to want to choose ones that I already know the way the system responds to those simple signals. Because if I can do that, then I can use additivity, and I can use homogeneity, and I can use time invariance together to take my collection of simple inputs whose responses I know, scale them, shift them, add them up to determine the total response of the system to my more complicated signal. And that's going to be an approach we use several times over. Take a complicated signal, describe it with a collection of simple signals whose responses I know or can find easily. And if I can describe my input as a sum of weighted and shifted simple functions, the output is nothing more than a sum of equally weighted, equally shifted simple function responses. That's true if I have a system that's linear and shift invariant, because superposition holds for those systems and time invariance holds for those systems. So for example, if we have a complicated signal and we know its output, and I put a scaled version of that signal in, I know my output's going to be a scaled version of the original output. And if it's delayed and scaled, the output is a delayed and scaled version. And we know if we add up those two complicated inputs to create an even more complicated one, we already know, based on this former information, what the response to this more complicated one's going to be. It's going to be our original response plus a scaled and shifted version of it. And that's true. I can make those predictions because our system is linear and time invariant. So what we're going to do is break up our input signals into simple functions that we either ahead of time or easily can mathematically determine if I put one of those simple functions in, we see what the output is. We'll call it a simple function response. And if we delay our simple function by t1, we know our output will be delayed by t1 and have the same shape because it's a time invariant system. And if we scale the height of our input of our simple function, even the delayed one, we know the output's going to look like a scaled version of the delayed simple function response. So if I can take an even more complicated signal and describe it as a collection, a sum of scaled and shifted simple functions, and I know the response of the system to one of these simple functions, linearity and time invariance let me make this conclusion, that the output's going to be nothing more than a sum of equally weighted, equally shifted simple function responses. That's going to underlie the principle of convolution and superposition that we're going to use as one technique to determine the output of a system for a complicated input signal. And that only works because our system is linear and time invariant. Now, maybe a simpler way to illustrate this, how we would use superposition to find the response of a system. Let's say we had a simple RC circuit. And let's say this capacitor is discharged at time t equals 0. And I'm going to put an input signal to it. And if I put an input signal being a voltage, time varying voltage, and we measure what comes on the output across this capacitor and call that the output voltage or the output signal, V of t. And what if I put in a unit step into that function? So I'll put a step function in here, apply that to this side, and measure what comes out. And let's say it looks like that, kind of a slow rising exponential rise to reach the same level. And we determine or measure that it has this functional form, which it actually does. 1 minus e to the minus t over RC, where RC is the time constant of the circuit, times u of t, because I turned this thing on at time t equals 0. Now, what can I do with that information? Well, I could answer questions like, what would the system's response be to this now rectangular pulse function? A pulse with a height of 3 and a width of 2. We could predict, if we know the output to a unit step, we can predict the output to things that look like unit steps. I could describe my input signal as a sum of weighted and shifted unit step functions. This would be like a 3u of t minus 3u of t minus 2. So this u of t to turn it on, this one to turn it back off. So I've described my input, a sum of weighted and shifted unit step functions. I chose these functions because I already know the response of the system. I've measured it before to just u of t. So if u of t produces this response, if I put in 3u of t, I get 3 of these responses. And if I put in u of t minus 2 to the system, I get this same response delayed by 2. So everywhere there's a t, I put in t minus 2. And if I scale that by minus 3, I scale this response by minus 3. So if this is my input signal, and this is the response to u of t, the response, the output of this system is going to be 3 of these minus 3 of these time shifted by 2. Or, writing that out explicitly, 3 times my s of t, 1 minus e to the minus t over RC u of t, minus 3 times s of t delayed by 2. So we replace all the time arguments with t minus 2. And this would be the total response of this system to my pulse input. So by describing a more complicated input with some simple function, that I chose because I knew the response of the system or had measured it before to that particular input, I can use homogeneity to multiply my signal and multiply my response. I can use shift invariance to delay my input and therefore delay the response. And I can use additivity, because we have a linear system, to add up the individual responses to the individual inputs. And so because I have a linear time invariant system, I can make these predictions. That's why we're looking for those kind of systems. Now, in all these different classes of systems, where do they show up and which ones are we more likely to run into in the real world? Linear systems, very often actually. And in fact, even when systems are nonlinear, because the analytical tools that we have for linear systems are so much easier and more powerful than the ones for nonlinear systems, even if we have a nonlinear system, we'll often model them using linear systems theory, because even nonlinear systems over a small enough range act linearly. And so over that smaller range, sometimes we can treat them like they're linear and use all these great analytical tools that we have. Are things time invariant? Well, usually. Practically, there is no such thing as an analog, truly time invariant system. If we think about our circuits that we build in the lab, they behave mostly time invariantly because we're looking at them over a small snapshot of time. If we were to look at them over a centuries-long length of time, well, then solder joints would start breaking down, things would start to corrode, the values of the resistors and capacitors would change as they absorb moisture. So technically speaking, very few things are actually completely time invariant. But again, over the narrow range of time that we're interested in, most of them can be treated as if they are. Are systems causal? Well, if it's a real-world system, something that operates with physical components, it has to be. We can't build systems that anticipate the future. Dynamic? Well, usually. Static systems are pretty limited, kind of boring, and so most of the systems we're going to run into are going to be dynamic systems, and certainly most in this course will be dynamic. So typical kind of system we're going to be operating with is going to be dynamic, going to be linear, going to be time invariant, most likely causal, and probably stable. What we need you to be able to do now is determine which of those classifications does it fall into, either when a system is described by its system operator, or more likely, when it's described by a linear constant coefficient differential equation. So we want you to be able to recognize from the differential equation describing a system's operation, whether it's linear or not, whether it's time invariant or not, whether it's causal or not, whether it's dynamic or static. We'll get some practice with that doing some homework problems, and we'll come back next time and start exploring some of the things we can do with our systems once we've classified them, particularly with our linear time invariant systems. What that enables us to do when we have this particularly powerful class of systems. So we'll see you next time.